We are at chapter 19. Chapter 19 at the textbook. Chapter 8 at my lecture. Yeah, it's planar kinetics of rigid body, impulse and momentum. So we're going to look at impulse and momentum, yeah, for a rigid body. So at the end of the lesson, you'll be able to develop formulation of linear and angular momentum for the body and apply the principle of linear and angular impulse and momentum. Yeah. The applications, one of the example is there are many things that's happening around us that has got application of linear and angular momentum. One of it is the swing bridge that opens and closes by turning. They are using the motor located under A. Yeah, this kind of bridges is rare in Malaysia. I don't think so we have any, but those countries with lots of canals, they have this kind of concept, yeah, where the bridge will actually turn. There are some will lift up, but there are some will turn, just totally turn to allow ships or small barges to actually pass through them. Yeah. So if the bridge is supported by the end of B here, yeah, would have the same torque to open the bridge at the same time, or will it be slower or faster? So yeah, another example is this Chap test that you have done in the lab. Yeah, so when it drops down, it has an angular momentum and a linear momentum. Yeah, angular momentum and linear momentum. So both. We can calculate the impulse and the pendulum exerts when it hits the test specimen. So as the pendulum rotates about point O, what is the angular momentum at point O? So these are the questions that you can answer at the end of the lesson. Another application is on the space shuttle, where space shuttle has several engines that exert thrust on the shuttle and when fired. By firing different engines, the pilot could control the motion and the direction of shuttle. Yeah, so that's one example. So let's go into our lesson. Okay, so we're going to look at linear and angular momentum. Linear momentum is something that you're very familiar with, which is your L equals to mv. Angular momentum is something which is new. So Ig is mass moment of inertia and omega will be the angular velocity. Yeah. Okay. So for the case where it only has translation, there is no rotation. I repeat, translation, there is no rotation. So your Hg becomes 0. Your L has a value. But there are cases where you have got both rotation about a fixed axis and also a linear movement at the same time, moving in a linear line and rotating about an axis. So you have both the components. Yeah, you need to write both the components. Okay. So, and general plane motion is subjected to both linear momentum and angular momentum computed at G, at point G. So that's the reason why this is L mvg and hg is ig multiplied with omega. Okay. So let's do an example 19.1. At a given instant, a 5 kg slender bar has a motion about figure 13.a. Determine the angular momentum at point G. So they want angular momentum at point G. Yeah, they want Hg and about the IC at this instant. So first thing to draw is, okay, you need to visualize that when VA actually drops down, B will be moving in this direction, right? So if you draw this, what do you get? Yeah, we have VA, which is pointing downward. We have VB pointing here. Okay, now VG slanting at this direction can be a bit tricky. So what you need to do is, you need to, okay, let's say this is, you redraw this rod, yeah, in a way that it is shifted down. Yeah, when it's dropping, it's like, it's dropping like this, right? So if you see this VG, you use a ruler, you measure nicely and you draw, you will see the VG is actually slanting downward like this. So that is how you get the speed of VG moving down. It's very important, yeah, to actually draw correctly, because otherwise you'll get into trouble. Okay, the angle is given here as 30. So if you were to redraw this, there's 30 here, you will see that up here will be also 30. VG, the what do you call it? It's right in the middle. So it's 2 meter here, 2 meter here. Yeah, you need to split that. Okay, and you have to use a bit of trigonometry here to actually what you call to actually draw this. Now remember how to draw the IC from the tip to tip. Yeah, just tip of the velocity. Yeah, and the tip of the velocity, you will see that IC is actually joining here. So from there, you know, you can actually see that the IC has to be 90 degrees. Always remember 90 degrees at all portion. So this will be 2 meters here, 2 meters here, 2 meters here. So this height, this length here will be 4 meter cos 30. How do you get that? Because it's, I'm going to use another pen. 4 meters. The angle is actually 30 here. So 4 meters cos 30. Okay. Okay. So that's done. Okay. Let's see. Erase everything. Okay. So it's clearer for you to see now. Okay. So you know this. You know this 30. Yeah. 2 meters here. Okay. Everything you know already. Okay. Now let's start solving the question. Yeah. You want to find the omega. Remember one thing. Yeah. Omega is the same throughout. If you're looking, you are using A to look for the omega, it will be the same. Omega here, as long as it's the same rod. Okay, so you can actually use A. This one is actually using A to find for the omega of the rod. So from the formula of V equals to R omega, if you see here, what is the V given in the question? Yeah, initial V of VA is 2 meter per second. So 2. And what is the radius? 4 meter cos 30. Yeah, so you have your omega. Omega will be 0.5. So you use that omega to actually find for the VG. So VG's velocity would be 1.155. Okay, so that is how you do. Yeah, because the omega is actually applicable throughout the whole rod, as long as it's the same rod, but the velocity at different points can be different. Yeah, so you see, like example for these, the velocity A is 2. The velocity of VG is 1.15, even though it's the same rod. So the velocity is not the same. It will never be the same. Yeah, I mean, not to say never be the same. Sometimes it can be same, it's coincidence, but most of the time it's not the same. But the omega will be the same as long as it's the same rod. Okay, so to answer the question is actually asking what is the HG, right? HG. So we have got our VG. Let's calculate. So HG is IG omega. So what is IG? For a rod right in the middle, it's 1 over 12 ml square. 1 over 12 ml square. Yeah, multiply with the omega, the what you call the omega. So omega is the same for the rod. So you have this value of 3.85. Yeah, 3.85 for the HG. Okay. Now the next part is to find for the IC, omega at IC. So what we have here, IC is shifted, and the distance is actually shifted. It is not what you call on the rod itself. It is a distance away. So if you look at the formula in the textbook here, I'll just tell you which page that you should go to. If you see page 521, yeah, page 521. Now, if you go to your textbook, page 521, yeah, you will see this formula down here. HA equals to IG omega plus D MVG. Okay, so, and the next line will be HIC, which is IC omega. Yeah, so this one is the breakdown for the IC, means a different point from the G itself. Now, moving on to our example question here. So this is to solve. So can you see the formula here now? Yeah, the formula here similar to the textbook formula. Okay, so let's fit in values, yeah, into the what do you call the formula itself. So they want at IC. Yeah, they want at IC. Let me erase all this so that it doesn't look too messy. You've got a lot of things here. Okay. So IG omega, 1 over 12 ml square plus with omega, which is 5.774. And then we have D, distance D. G to D, to IC, sorry, that is the distance, which is 2 meters. Multiply with the mass, which is 5 kilogram. Slender rod, 5 kilogram. Yeah, M. Now VG, what is the velocity at the G? We have calculated this previously. So when you plug in all the value, you will see that it is 15.4 kilogram meter square per second. Now there is another alternative method to use this. This is an alternative method. Yeah. So what happens here is that, can you see this portion is your IC portion. Okay, you remember the old formula in the chapter, which is like parallel axis theorem, 1 over 12 ml square plus with md square, okay, multiply with omega. Yeah, so they find the IC and then they multiply with omega. We can use that same method as well, yeah, because the standard 1 over 12 ml square is in the middle, but now the axis has shifted here. So this will be the distance, yeah, that's why it's 5 multiplied with 2, yeah. Okay, so this is the end to this first video. I'll see you in the next video, yeah.